EigenFish, and it's an unsupervised linear image-to-image translation algorithm. Our work builds upon a previous paper, and actually makes it much better. But the general idea of this algorithm is that we have some kind of image translation that we want to do without pairs. So maybe it's super resolution, maybe it's inpainting, or maybe it's colorization. And instead of one of those, I decided to make a test case that's really hard. It's actually colorization, super resolution, noise, and inpainting all at the same time without pairs. And the result is their algorithm didn't do very well. This is their results. And these are our results under the same circumstances. Here's some more test results. So basically, the general idea of our algorithm is that when you have two images that are close in PCA space, they're also close in image space. So if you have two similar looking images, their PCA embeddings are going to look pretty similar. And so by translating images' PCA embeddings, we can translate images. So let's say we have two image domains, A and B. In this case, A is grayscale and B is color. If we take the PCA embeddings from a grayscale image and translate it to an embedding in the color image PCA space, then we can translate images. Now remember, PCA embeddings are all vectors. And to transform a vector, you can multiply it by a matrix. And for our linear image translation algorithm, we call this matrix Q. And Q is the only variable that we try to solve for. It's the only thing that our algorithm learns. And so, what exactly does Q do? Well, let's say we have a set of embeddings from domain A, ZA, and a set of embeddings from domain B. Q translates ZA into ZB like this. Alternatively, we can write ZA as this. This is what it's defined as. All the images multiplied by their principal components are their embeddings. W is their principal components. And here's what they look like. You may remember eigenfaces from class. This is what WA looks like, and this is what XA looks like. XA is a matrix, where the first dimension is the number of images, and the second dimension is the dimensionality of these images. Note that each image is flattened out into this matrix before it was translated. And here's how we take that embedding translation and we turn it into an image translation. It's just a little bit of linear algebra trickery. And then we have some black and white images here that get turned into XB, or domain B, over here. So here's a rundown of the feed-forward part of our algorithm. Let's say we take image number 23 from domain A, this black and white girl. What would we do with her? Well, we have two sets of filters, orthogonal basis 1 and orthogonal basis 2, called WB and QWA. First, we take the dot product of this image with all of the first filters. We're taking it, we're multiplying it, and we're getting the sums. Note here that black means negative and white means positive, because these images are actually all normalized before we do PCA. After we have these embeddings, we then take these numbers and we go to the corresponding embedding in WB. And we multiply WB by that number, and then we add the results all up together to get our color image. And then we do that for all of the images. And then we compare our outputs to the targets. We use mean squared error to figure out the difference between these two. And then we backpropagate Q to make the error go down. Ta-da! We solved it! Not so fast. Actually, the whole point behind this algorithm is that it's unpaired. So, if there's no pairs, how do we get the error between these images? How do we backpropagate Q? The answer is Earth mover's distance. Earth mover's distance is a metric that can measure the distance between two unlabeled point clouds by using optimal transport. And so the idea is that first we take all of our outputs and we take their embeddings, and we take all of the true targets and we get their embeddings. There are no matches, but they should have similar point clouds. And then we feed it into Earthmover's distance, and we use that as a loss to adjust Q, and make the error go down. However, there's a bit of a catch here. Whenever you're trying to do unsupervised point matching, it tends to be an NP-hard problem, and it gets stuck in local minima all over the place. So, to combat this, we need a good initialization. As it turns out, when you solve it in a paired setting, this is what the result looks like. QWA. This is what the approximation of WB looks like. You'll note that the eigenvectors of domain A don't exactly match up with the eigenvectors of domain B. In fact, it actually skips a few, because domain B has more information. Domain B has colors. And you can see that domain A just can't keep up with it, and so not all of these eigenvectors match one-to-one. So the solution is that we force them to match together by projecting all of domain A's eigenvectors onto domain B's eigenvectors. This is the second large improvement upon the previous paper. And that's our presentation.